Acids and bases. Some definitions. The classic definitions of acid and base were proposed by Arrhenius. According to Arrhenius, an acid is a substance that increases the concentration of hydrogen ions when dissolved in water, and a base is a substance that increases the concentration of hydroxide ions when dissolved in water. These are the classic definitions of acid and base. They allow us to indicate that a substance is an acid or a base by how we write the formula. Acids are written with hydrogen as the first element because they will form the hydrogen ion, H+. Bases are written with OH at the end because they form the OH- or hydroxide ion. These definitions are still used today when dealing with strong acids and bases, and when doing stoichiometry calculations, as for acid-base titrations. In a classic acid-base reaction, an acid reacts with a base to produce water and a salt. Not all substances that produce an acidic solution, or a basic solution, fall under the Arrhenius definitions. For example, a solution of ammonia, NH3, is significantly basic without containing the hydroxide ion, and a solution of CO2, carbon dioxide, is significantly acidic without containing the hydrogen ion. Independently, Bronsted and Lowry proposed that the essence of acidity was the transfer of a hydrogen ion, H+, a proton, from one molecule to another. This gives rise to the definition of an acid as a proton or H+ donor, and a base as a proton or H+ acceptor. A Bronsted acid must contain hydrogen, and the hydrogen atom must be removable. Not all hydrogen atoms are removable. For example, most hydrogen atoms in organic molecules are not removable because the carbon-hydrogen bond is too strong. A Bronsted base must be able to bond to the proton, and this happens when the molecule has an unshared pair of electrons. Any molecule with an unshared pair of electrons can act as a Bronsted base because the proton will attach to any unshared pair of electrons. Many particles have both removable protons and an unshared pair of electrons. These molecules are called amphiprotic substances. Some examples are HCO3-, HSO4-, and H2O. Note that the particle can act as either an acid or a base, but in any particular reaction it will only act as one of the two, depending on other factors. What happens when an acid dissolves in water? When an acid like HCl dissolves in water, the water acts as a Bronsted base, and a proton is transferred from the HCl to the water. This leaves us with the conjugate base of the acid, in this case the chloride ion, Cl-, and the conjugate acid of the base, the hydronium ion, H3O+. The word conjugate comes from the Latin word which means to join together. The conjugate acid and conjugate base are what we have after the transfer of the proton. The Bronsted acid loses an H+ and becomes its conjugate base. The Bronsted base gains the H+ and becomes its conjugate acid. In a Bronsted acid-base reaction, an acid reacts with a base to produce the conjugate base and the conjugate acid. There are two problems on the problem sheet for this lesson that deal with determining the conjugates. The strength of an acid and the strength of its conjugate base, or a base and its conjugate acid, are related to each other. the strength of an acid is related to how tightly it holds on to the proton that can be donated. The weaker the hold, the more easily the proton is donated. So the weaker the hold, the stronger the acid is. The stronger the hold on the proton, the easier it is for the base to accept a proton. So the stronger the base is. Strong acids are completely dissociated in water, so their hold on their protons is very weak. Therefore, their conjugate bases are extremely weak, to the point where they will not generally act as Bronsted bases. Weak acids only partially dissociate in water, so their hold on their protons is moderate, and their conjugate bases are weak bases as well. Substances with negligible acidity essentially do not dissociate at all, so their hold on their protons is very strong. Therefore, their conjugate bases are very strong. In general, the stronger an acid is, the weaker its conjugate base, and the weaker an acid, the stronger its conjugate base. In a Bronsted acid-base equilibrium, all four particles are present. We have the acid in the reactants and the base in the reactants, and the conjugate base and conjugate acid in the products. Will we wind up with more of the reactants or more of the products when we reach equilibrium? The stronger acid, the one that holds the proton more weakly, will be easy to remove the proton from, and the stronger base, the one that holds the proton more strongly, will easily accept the proton. Whichever side of the reaction the stronger acid is on, it will lose its proton more easily than the acid on the other side. So we will wind up with more of the weaker acid and weaker base at equilibrium. Consider the reaction for the dissociation of HCl and water. HCl is a strong acid, so Cl- is negligibly basic. Water is a stronger base than Cl- because H2O is a weaker acid than HCl. Therefore, we end up with mostly H3O+ and Cl- at equilibrium. In fact, there is so little HCl left that it is not possible to determine its concentration, or the value of Ka for this equilibrium. It is too large. On the other hand, acetic acid, HC2H3O2, a weak acid, does not dissociate very much in water. The acetate ion, C2H3O2-, is a stronger base than water, so we end up with more acetic acid and water, and the value of K is less than 1. The strength of an acid is strongly connected to the equilibrium constant for the dissociation reaction. For this general reaction, where HA is any general acid, the equilibrium constant is Ka equals the concentration of H3O+ times the concentration of A- over the concentration of HA. The stronger an acid is, the more it dissociates in water, and the larger the numerator in the equilibrium expression is. The larger the numerator, the larger the value of Ka. So the stronger the acid, the larger the value of Ka. There is a table of the values of Ka as an appendix in your textbook. There are two problems related to acid strength and the Bronsted acid-base reactions on the problem sheet for this lesson.